Hello everyone and welcome to video number 5 in the FEMM 4.2 course. In the previous video, we covered an electrostatic application for the trough tester problem, but here we are going to cover another electrostatic application for underground cables. So let's start. For the underground cable shown in the below figure, we need to model the cable using FEMM 4.2 as an electrostatic planar problem. All dimensions are given in millimeters. So what do we need? We need the electric potential and electric field through the control lines, and also we need to calculate the capacitance. So if we look for the problem, we have here R1 is the inner radius, R2 is the outer radius, and we have insulating material, PVC material with permittivity epsilon 1 equals 2.5. So please don't forget that epsilon, the permittivity, equals epsilon node epsilon R. Here epsilon R equals epsilon 1, but epsilon node is the permittivity of air equals 8.85 10 to the power minus 12 farad per meter. So the cable has 1 kilovolt, so the voltage for this cable is 1 kilovolt, and the conductor here is copper conductor. Definitely this point is connected to the ground, so we are going to simulate that one. But before simulating the cable using FEMM 4.2, we need to anticipate the results. Here we are going to put the equations for the underground cable as a fact. I presume that you covered electrostatic course before. If you didn't cover an electrostatic course before, I'm going to give you the formulas, how to calculate the electric field and how to calculate the voltage. There will be another course explaining from where these equations come from. But here we are going to have it as a fact. So electric field E equals Q, which is the total charge, over 2 by epsilon. Epsilon equals epsilon node epsilon R, x any distance between small r and capital R, which is the inner radius to the outer radius, in the direction of AR. So this field is radial. So E is volt per meter, so the voltage will be the integration from R to R, Q over 2 by epsilon x dx. So in this case, voltage V equals Q over 2 by epsilon natural log R over R. So what is the relation between E and V together? So the electric field E equals the voltage V over x any distance from R to R, natural log R over R. So this equation can give us the electric field at any point inside the cable, and also we can find the distribution of the voltage from the center of the cable to the outer radius. So to find the maximum and minimum electric field, so E maximum equals the voltage V over x equals small r, which is the inner radius, multiplied by ln R over R. So if we calculated that one roughly, so the voltage is 1000 volts, R equals 20 millimeter, natural log 2, so this one gives you around 70,000 volt per meter. So E minimum equals V when x equals capital R, so V over R natural log R over R as well, so that one in the range of 36,000 volt per meter. Fine, so how to calculate the capacitance? So the capacitance equals Q over V, and in this case 2 by epsilon natural log R over R. So the capacitor of this cable should be in the range of 2 nanofarad if we're going to have epsilon R equals 2.5. So look for the distribution. This is what we are going to expect to see from the FEMM, that we have here a maximum and minimum point for the electric field, and inside the conductor the electric field should be 0, and the voltage should be 1000 volt and going up to 0 point because this point is connected to the ground. So let's go to the FEMM and simulate this cable and try to confirm these results. This is the underground cable we want to analyze, so I drew the cable here. So if you don't know how to draw it, please refer back to videos number 3 and 4. I'm going to leave for you in the comments the links for these videos. So the problem is a planar millimeter. Definitely the problem can be solved with axisymmetric, but I'm going to solve it as a planar, and the depth is 1000 millimeter. Okay, for the grid size I choose 10 millimeter. So that one is 1020, so the inner radius is 20 millimeter and the outer radius is 40 millimeter. What about this circle? That one is a boundary. So I adjusted this circle for 1000 volt and that one for 0 volt, and definitely the boundary is 0 volt. Regarding the material, let's go for the properties menu, materials. I choose air, PVC, copper. So I'm going to click on PVC, modify property. If we look here, I adjusted the epsilon R, which is permittivity, 2.5 in X and Y direction. So let's click OK. So now that's all the materials are added. That one one is copper material, that one is PVC material, and that one is air material. So now we can create our mesh. We are going to click here. So we have 7,493 nodes. We are going to analyze. Either click here for analyze or click on this button. So we click on that one. So the problem will be analyzed now. So it's finished. We're going for this Google to see the results. This is the results for the underground cable. So as we can see here, the voltage inside the conductor is 1000 volt. If we click here for any point, so that one is 1000 volt, and the electric field inside the conductor is 0. At the inner radius where R equals 20 millimeter, so if we click on that one, so that one is 1000 volt, and the electric field start to be the maximum electric field. After that one, the voltage is going to be reduced until we reach to this point, which is 0 voltage. So what will be the pattern of the voltage? We need to use one of the contour lines, either the vertical or horizontal, because that one is circular, so those are identical. So we are going to use the horizontal one. So click on line, click on this point to this point, then we are going to plot the voltage. So what is the voltage? So the voltage is 1000 volt inside the conductor, and then the voltage will be reduced until we reach 0 voltage. What about the electric field? Is the electric field as expected? Let's look. So that one is the electric field. Here we have 0 electric field inside the conductor, and we have maximum electric field 72 kilovolt per meter, and the minimum electric field is 36 kilovolt per meter. That one is expected. We calculated because E equals V over R1 natural log R2 over R1. If we use the equation, so that one give you almost the same results. So the finite element analysis matches the hand calculation in this case. What is the cable capacitance? We are going to click on this icon now, the capacitor icon. So that one is going to give you the voltage 1000 volt, and the charge is 0.2 microcoulomb. So the capacitance C equals Q over V. 0.2 over 1000 volts, that one gives you 0.2 nanofarad. If we're going to use the equation, C equals 2 by epsilon node epsilon R over natural log R2 over R1, that one is going to give you the same results exactly, 0.2 nanofarad. Okay. Let us learn something new here in this video. In the previous video, I didn't cover this arrow. So what will happen if I click on that one? So click on that one, we're going to see vector plot. So we are going to open this menu. We're going to choose, for example, the electric field. If we click OK, we're going to see the direction of the electric field as radial direction. So that one shows to you where is the electric field direction. So you can enable or disable. So I'm going to put that one none now. Okay, I'm going to look for another thing for the result analysis. What will be the case if the permittivity of the insulating material is changed from 2.5 to something like 4? Let us see. So I can remove the mesh now. So mesh, merge mesh. So this means that we have no mesh now, but we need to change the PVC properties. So going for the properties, materials, choose PVC and then modify property. Rather than we have epsilon R equals 2.5, I'm going to make that one 4 and 4 in both X and Y direction. Okay. Okay. Click mesh. Okay. Run. And we are going to see the results. We didn't feel there is any difference if we change the PVC permittivity from 2.5 to 4. Please don't forget that we apply the voltage to the conductor, so that one is 1000 volt, definitely is going to 0. But the electric field, maximum and minimum, will be changed. Let us check. So we are going to choose this contour, and then we are going to plot the electric field. We are going to see that the electric field have the same results, no change. So let's explain that one. If you look for the equations here, E maximum equals V over R1 natural log R2 over R1. So that one is not affected by epsilon. And E minimum equals V over R2 natural log R2 over R1. That one is not affected by the permittivity. So we expect that the electric field maximum and minimum will be the same. So the electric field will be affected by the size of the cable. But what will be the effect? So let's click on this capacitor. So the voltage is 1000 volt, but we find that the charge is changed. So this means the capacitance of the cable will change. So that one will be 0.32 microcoulomb, and that one is going to give you a capacitance 0.32 nanofarad per meter. So the effect of the permittivity is going to affect the capacitance of the cable. Let us return back to our schematic. I'm going to close that one now. So we have here our cable. Inner radius is 20 millimeter, outer radius is 40 40 millimeter. So what will be the case if we change, for example, the outer radius? So definitely that one going to affect the maximum minimum electric field. So I'm going to choose the outer radius, something like 54.37 millimeter. Why specifically this value? So that one gives you R2 over R1 equals 2.7183. What's 2.7183? So that one is called Euler number or Napier's constant. So natural log for 2.7183 gives you 1. And in this case, the voltage and electric field has a linear relation where V equals EX or E equals V over X, inverse function. So let's do that one together. I'm going to remove the mesh, click here on that one. So tab 54.37 and 0 point. So that one is the point for the outer radius now. I'm going to choose another one, minus 54.370 as well. Choose arc, connect between this point and this point, 180 degrees. That one is a top semicircle, and connect this one to this one. So that one will be the bottom semicircle. I'm going to remove this one. I'm going to select this one. Remove. So what I need now, adjust outer circle to be low voltage. So I'm going to choose that one and that one, space bar. So that one will be in conductor but low voltage. So if we're going to create the mesh now, so we have the mesh, then we are going to run. What will be the results? So we have the voltage, as we can see here, from 1000 volt up to 0 volt here. And that one is expected. But I'm going to choose this line, connect from this point to this point, and let us see what will be the electric field. So the electric field changes from 72 kilovolt per meter to 50 kilovolt per meter, and the lower one, something like 18 kilovolt per meter. So is that expected? Yes, because if you have the voltage 1000 volt and the inner radius is 20 millimeter, so the electric field should be 50 kilovolt per meter. And the outer radius is 54.37, so that one gives you roughly something like 18 to 20 kilovolt per meter. So it's clear that finite element analysis or FEMM confirms the hand calculation. Let us return back to our slides. Here we're going to have another application, multi-layer underground power cable. For multi-layer, 2 layers, 3 layers, 4 layers, we're going to have an example here for 2 layers. Layer number 1 has epsilon 1, where epsilon 1 equals epsilon node epsilon R1. And layer number 2 has epsilon 2, where epsilon 2 equals epsilon node epsilon R2. So in the cable here, we're going to find that this point, or this is a conductor, so this point has maximum electric field. So if we take a horizontal contour, so that one is E1 maximum. Why we call it 1? Because this is layer number 1 and has a specific epsilon 1. And definitely this point is E1 minimum, because we have another epsilon for this layer. So we have at this point another E2 maximum until we reach E2 minimum here. The cable voltage from V here up to 0, because that one is a 0 voltage. So what are the equations? E1 maximum equals Q over 2 pi epsilon node epsilon R1 R. And for each E, that one, it depends on the layer, where are you? For the voltage V, that one equals Q over 2 pi epsilon node 1 over epsilon R1 natural log R1 over R plus 1 over epsilon R2 natural log R2 over R1. So how we are going to find E1 maximum in terms of V? So V1 equals E1 maximum R natural log R1 over R, or E1 maximum equals V1 over this expression. And V2 equals E2 maximum R1 natural log R2 over R1, and also V1 plus V2 should equals the voltage of the cable V. So we need to simulate that one using finite element analysis or FEMM4.2 and make sure this one was going to satisfy the hand calculations. So let's take this example. With an external insulating layer as shown in the below figure, we need to plot the electric field across the contour line. So that one is the contour line. What is the voltage of layer number 1? So our task is just to know the voltage of layer number 1, the voltage of layer number 2, and make sure that V1 plus V2 should equals the voltage V. So the cable voltage is 1 kilovolt. The inner radius will be 20 millimeter. So the radius of layer number 1 is 40 millimeter, and the radius of layer number 2 is 50 millimeter. millimeter. The insulating material here, number 1, is PVC. We call it PVC1 with epsilon 1 equals 4. And that one I'm going to call it PVC2 with epsilon 2 equals 3. So let's go. This is a multi-layer cable. As we can see here, we have a conductor, copper conductor with 1000 volts. So we are going to adjust this layer with 1000 volt. We call it high voltage. So we have here layer number 1 with insulating material PVC1. So relative permittivity is 4. And for layer number 2, relative permittivity is 3. Here we have air and the outer circle is the boundary. So let's go for the properties, materials. I'm going for PVC1 modified property. So I adjusted that one to 4, and for PVC2 modified property I adjusted that one to 3. So now we can create the mesh, run our simulation, and now we can see the results. As we can see here, we have the voltage changing from 1000 volt up to 0 volt. But what is the voltage of layer number 1? What is the voltage of layer number 2? So I need to measure the voltage of this point. So I'll make sure that's snap to grid. I'm going to click view, points prop. So I'm going to click on this point. So that one is 300.457 volt. But this is the voltage of this point, and the voltage of this point is 1000 volt. Click here, 1000 volt. So the difference between those two will be the voltage of layer number 1. So 1000 minus 300.457 gives you 699.7 volt, and the voltage of layer number 2 will be 300.457 minus 0. So if you add 699.7 plus 300.457, that one gives you roughly 1000 volt. So we checked for the first thing, that's V1 plus V2 equals V. So what is the electric field? I'm going to click on this line. I'm going to put a line here. I'm going to have the graph of the E, magnitude of the electric field. So that one shows to me we have E1 maximum 50 kilovolt per meter, E1 minimum something like 26 kilovolt per meter, and we have E2 maximum something like 34 kilovolt per meter, and E2 minimum will be something like 30 kilovolt per meter. So we have E1 maximum, E1 minimum, E2 maximum, E2 minimum. So we can calculate those using these equations. So we have here the equations. We can calculate E1 maximum, E1 minimum, and so on. Another question, what is the capacitance of the cable? So if we click here, we're going to find the voltage is 1000 volt and the charge is 2.247 10 to the power minus 7, or we can say 0.2 microcoulomb. So C equals Q over V, but we can calculate it using layer number 1 and layer number 2. Don't forget these two layers are in series. So for layer number 1 we have capacitance C1, and for layer number 2 we have capacitance C2. So C equivalent will be the equivalent of these two capacitors are in series. Capacitor in series like resistors in parallel. So C equivalent equals C1 C2 over C1 plus C2. So how to calculate C1? So C1 is the charge Q over V1. And how to calculate C2? The charge Q over V2. So once you know C1 and C2, you can calculate the equivalent capacitance of the cable. In this video, we examine and discuss the underground power cable, which is simulated using FEMM 4.2 as an electrostatic application. The results and analysis demonstrate how to plot the voltage distribution, electric field distribution, and electric field vectors. FEMM 4.2 is also used to evaluate the cable capacitors. The effect of the insulator material permittivity is discussed. The influence of cable dimensions on the electric field distribution is examined. Finally, the study is extended to a multi-layer underground power cable to show its effect on the electric field distribution. What will I watch in video number 6? In video number 6, we are going to cover electromagnetic application. See you in the next video.